Hey everybody, in this video we're going to talk about units of measurements, scientific notation, and orders of magnitude. So here you can see a list of our objectives or standards for this part of the chapter. We're really going to be looking at the fundamental units that we use in the IB or the SI unit system. We'll be talking about scientific notation, and as we begin to talk about these things, we'll talk about significant figures, rounding off our measurements, and also what it means to give a measurement to an approximate number and the difference between measurements and estimations. As we go through this video, we'll have these three questions that we'll reflect on at the end to kind of understand how units can impact what we're doing. So why do we need standardized units of measurements? Do they bring an advantage or disadvantage to science? How does what I measure influence how I measure? So a good example of this question might be, how does measuring a physical object such as, a table, how do we proceed with this measurement versus how do we proceed with measuring the distance of the Earth to the sun or the distance of Miami to Tampa? We can't simply just lay a meter stick out like we can to measure a table. We have to come up with various methods. And then finally, what is a fundamental unit? So here, ladies and gents, we can see a mind map of our fundamental units. So we see concentric circles, 3 to be precise, with SI in the middle. Now, SI stands for the International System of Units, which is originally from France, so it is called the Système International, hence SI. Now, the second circle is actually the most important because all fundamental units, by definition, are derived from a fundamental constant. That's what that second circle is. That's what the center circle represents. Each unit has its own fundamental constant. Now, these constants have changed as our understanding of things have changed throughout science, but that is the idea behind fundamental constants. Here you can see the actual breakdown from your Cognitive textbook. So each fundamental unit or quantity is represented by a symbol and is also defined with reference to something specific. And I'll tell you a little bit more about that on the next slide. So our fundamental quantities are time, distance, mass, current, temperature, the amount of a substance, and also luminous intensity. I'm going to go ahead and tell everybody right now, the candela or luminous intensity is not something that we'll be using in the course, but it is a fundamental unit. So we just got to be aware of it. Now, we're familiar with all of these base units over here. There may be one like the candela that you're not very aware of, but that's perfectly fine. The base units are all based off their defining constants. Now, as you can imagine, we have had the kilogram for quite some time. The original kilogram actually sat in a museum, I believe in Italy or France, for years, and it was the official kilogram of the world. But as time has progressed and we've begun to understand more about quantum mechanics, we actually now define the kilo in a quantum perspective. The same thing with the meter. The meter was originally the distance from the equator to the North Pole divided by 10,000. Now that we've discovered the fundamental constant of the speed of light, we use that to define what the meter is. The second also has an arbitrary definition, but now that we've begun to learn more, we've actually discovered that atoms vibrate at specific frequencies, and we utilize the frequency of cesium atoms to create the most accurate clocks in the world. Now, the question here is, why do we have to go through all of this push and shove and constant redefining of units? Well, the answer is actually really, really clear, ladies and gents. It is an international system of units. We are an international global scientific community, and we all need to have the same units that we work under. And if you're really, really curious about what I mean, what you should do is you should go Google the Mars Climate Orbiter. Yes. The Mars Climate Orbiter was sent up, I believe, in 1998 by NASA. And as it was trying to create its orbital path around Mars, it had pretty much no idea where Mars was and crashed right into it. The issue that NASA eventually published in all of its embarrassment was that they didn't double check the units. Some engineers had done calculations in different units, and the orbiter wasn't able to work properly. So millions of dollars gone. Hopefully somebody got a reassessment on that one. Now we have to acknowledge something right away. One of our first, or the very first fundamental unit, the kilogram, well, gram is the fundamental unit here, and kilo is a prefix. All right, and we utilize these prefixes before a unit to talk about the order of magnitude, or how many zeros there are in front of or behind that number. So we've all had some sort of introduction to these Latin prefixes before, but this is something that we're actually going to explore quite extremely in physics. We will quite literally be talking about from one topic to another, ladies and gents, or within the same topic, we can actually talk about everything from a femtoscale and particle-to-particle interactions all the way up to the exascale, where we are talking about, planetary movements and things like that. So we'll actually be talking about some of these concepts or these different types of numbers within the same unit of study. So it's really important we have a nice grasp on these right here. So our prefixes, our Latin prefixes, we're going to want to be very familiar with those, and also familiar with the scientific notation value that it brings. So one thing that you're familiar with and you've seen before in class is we typically will write a number like this, like 1.5 times 10 to the power of 6, right? This would be the same thing as saying, if this was in grams, this would be the same thing as saying 1.5 times 10 to the 6 megagrams, right? So this is a nice, easy tactic for us to use, shorten what we write. But I also wanted to let you know, ladies and gents, instead of writing times 10 to the 6, you can also write 1.5 capital E to the 6. And this is also the button you can use on your calculator to make the process a little bit easier for yourself. So both of these stand for our scientific notation. And this is something we're going to want to pay attention to, ladies and gents. Not only do we have to know our prefixes and how they apply to units, we've also got to be able to do some math. All right, ladies and gents, so I want to put this into practice and do a couple little problems just to give you a little familiarity with it. Now, remember that when we are dealing with scientific notation, if we have something such as times 10 to the positive 3, this number represents our decimal moving 1, 2, 3 places, okay? A positive exponent means our decimal is going to move to the right. If we have a negative exponent, that means our decimal is going to move to the left. Okay? So this is what we're looking at here, ladies and gents. And let's just do a couple problems, make it nice and quick. So the distance from London to New York is 5,585 kilometers. We know that kilo represents times 10 to the 3. So just like our example here, we're going to add 3 decimal spots. 1, 2, 3, 0, 0, 0. So we know that it is 5,585,000 meters from London to New York. The height of Einstein is a really easy one, so I actually want to move to number C because it's a unit we don't see that often. The thickness of a human hair on average is about 25.4 fancy U meters. This Latin letter here is mu, and we actually say here we call this micrometers. Micro stands for times 10 to the negative 6. So what we need to do here is we need to move our decimal spot to the left 6 positions. 1, 2, 3, 4, 5, 6. And there's our decimal spot. So we can rewrite this as 0.0000254 meters. We can also kind of see the importance now of significant figures and scientific notation. What's the point of wasting this time of writing so many zeros? And this is just the thickness of human hair, ladies and gents. Imagine scientists who have to study things like on an atomic level, or scientists who study things on a universal or cosmic level. We don't want to waste time writing all this. So understanding our scientific notation is a very important tool. So I also wanted to present you with the opposite of that, ladies and gents, and make sure you had examples of converting to scientific notation. Here we can see 2 simple examples, one with our exponent going up and the other with our exponent going down. So just a little practice here, ladies and gents. If you want to pause, go through these little problems right here, give you a little brush up on your standard notation and Latin prefixes. I also wanted to give a quick review of significant digits before we moved on, just so as we are simplifying and creating scientific notation, we're not cutting off valuable information. And that's really what significant digits show us. I do want to add one more rule though, and that rule has to do with multiplication, division, addition, and subtraction. When we are doing math with significant figures at all, there's a very, very basic rule. You always keep the least number of significant figures. Now, the reason behind this, ladies and gents, is really just the logic of a chain is no stronger than its weakest link. Okay, if we are trying to report an answer, well, our answer is no more precise than the least precise number. Okay, so if we want to do any mathematical operation, for example, with the numbers 1.25 and 1.5, we want to multiply them, divide them, add them, subtract them. No matter what you want to do, there are only, or the least number of significant figures is 2. That means that your answer must be reported to 2 significant figures. Our answer is only as strong as our least precise data point. And that's also something we'll talk about as we design labs in the future as well. As we continue to try and manipulate our units, the next step, as opposed to turning a meter to a kilometer or a gigameter, the next step is to turn meter into area, meter into volume. We turn mass and volume into density. These types of manipulations create for us what we call derived units. And these are the two main categories of units. You have fundamental units based off of a fundamental constant, and everything else is derived. You can also see, ladies and gents, that as we manipulate our units, the same tools may not be as useful. A meter stick is a very useful tool for finding the length of a normal-sized object or the area of a normal-sized object, but it is not useful for finding the volume of something. And it certainly can't really help you find the density. So as we change our units, we also have to imagine what we're measuring and how that's going to affect our approach to the situation. As we manipulate our units to create new ones, we also have to keep in mind the scientific notation. How do we deal with scientific notation when we're multiplying and dividing? It's really, really simple, and there's a golden rule of keep it separate, okay? So what do we keep separate? You have a quantity, and you also have an order of magnitude. These are what you're going to keep separate. Your quantities will be multiplied or divided, and then your orders of magnitude, the times 10 to 17, times 10 to the 14, those numbers will either be added if you're multiplying or subtracted if you're dividing. So to finish this video off, ladies and gents, I wanted to go back to our enduring understandings and see if we could really find an answer to these questions. So why do we need standardized units of measurement? Well, hopefully you went and looked up the Mars Climate Orbiter, and you can really start to see that as a global community, we really need to have some consistency. And that is really important, and where the definition of fundamental units has been important as we gradually broaden our understandings of topics. It's important that we all accept these new definitions to move forward. So how does what I measure influence how we measure it? Well, I think a great example of this might be an example of moving from meter to area to volume. For one of these, you might just use a meter stick. For area, I would prefer to take a photo of it and then use my computer to analyze the data. And then for volume, we might put something in a bucket of water and watch the amount of displacement that happens. So as we can see, what we are measuring will dictate how we measure it. And then the final question we want to ask ourselves is, what is a fundamental unit? Now, fundamental units all come down to the idea of constants. Each one of them is based off of a fundamental part of nature, whether it's the vibration of an atom, the speed of light, or something as bizarre as the Planck constant. We'll talk about some of these things or all of these things throughout the 2 years in this course. But for right now, ladies and gents, I want you to think about measurement. I want you to think about how we measure things and how the tools we use can affect that measurement. Our next video is going to be all about this idea and how we represent that in our data.